Hello folks, StylePoint here, and today we're going to be implementing distance functions, aka similarity functions. And so I already have the boilerplate for this ready. We have Euclidean distance, Manhattan distance, and cosine distance. And the way this is going to work is we're going to run this way. Well, actually, let's run it that way. So by default, it's going to run on what we have here. But once we implement any of these, let's suppose Euclidean distance, we can comment out this piece of code, line of code, and then we're going to get some values on the terminal here. Okay, so let's start with the Euclidean distance. And to do that, let's take a look at whatever we have on this Wikipedia page for Euclidean distance. So we can click on the image. Okay, I think this is a better way to visualize or think about Euclidean distance. Euclidean distance can be computed between 2 points, but we can think of these points as feature vectors or feature tensors in a way. And while the example here is going to be on a two-dimensional space, again, this can be generalized, and we can think of n-dimensional spaces, or we can think of order n tensors. So usually people use, I think, dimensions when talking about tensors, like two-dimensional tensor, but it's better to use term order. So we're going to say order 2 tensors, order 3 tensors, order n tensors, and in fact, order 0 tensors exist as well. They are scalars. So let's use that term moving forward, and let's discuss Euclidean distance. Well, Euclidean distance is the distance between 2 points, P and Q in this case, and you can see the way we can compute this is that we can construct this imaginary right triangle, and using the Pythagorean theorem, we can compute the hypotenuse, and that's basically the distance between P and Q. Now, this is also known as the Euclidean, well, people don't really refer to it as a Euclidean similarity, but it can be used as a similarity function. So the reason for that is because if the distance is 0, well, then P and Q is the same point. And if we have 2 feature vectors, let's suppose, I don't know, in this case, T1 and T2, okay, these 2 feature tensors, if the distance between them is 0, well, that means that they're probably very similar to each other, okay? And that's basically the way we can use Euclidean distance. If we have 2 tensors, we can compute the Euclidean distance. If the value is close to 0, well, we're going to say they're similar to each other, okay? And let's compute it. Now here we're using like two-dimensional space, or well, we're considering these points on a two-dimensional space, but again, this can be generalized, and we can think of n-dimensional space. Using NumPy, we can generalize this. Now, looking at this, they subtract the x-coordinates and then y-coordinates, square it up, and sum it up, and then we need to do square root to get the actual distance, because this is distance squared. But we can do it using broadcasting as well. We can do element-wise subtraction using broadcasting. And one way to do it is literally following the formula. It's T1 minus T2, right? And the 0th coordinates of T1 and T2 are going to be subtracted. The first index 1 coordinates are going to be subtracted, and we're going to get a tensor of differences pretty much. After we get that, we need to square it, and we need to sum it, and finally we need to raise it to the 0.5 power, right? So it's the square root from the sum of squared differences, and that's what we get here. And now we can comment this out and rerun it, and we get 0.4100. Now, this is actually not the way I implement this when I implement it using NumPy. I prefer another implementation, which, of course, is going to give us the same result, but it's a bit shorter. So it's kind of a more concise implementation of that. We're going to see that the result is going to be the same, 0.4100, but what we do is that we compute the norm of the vector between points T1 and T2. In this case, we call them, tensors, feature tensors, whatever. But if we have both of them, well, both of them will be on some dimensional space. Let's suppose n-dimensional space. We can construct a vector between T1 and T2, and direction of this vector does not really matter whether it's from T1. Whether it's pointing toward T1 or toward T2. In this case, it's going to be pointing toward T1, so it's going to have that arrow. The arrow pretty much is going to be toward the direction of T1. But again, it would be the same It does not matter how you do it, because again, the magnitude of the or the norm of the vector does not change. And why do we calculate the coordinates of this? Well, that's the way you calculate the coordinates of a vector. If you have point A and point B, in this case P and Q, you can calculate the coordinates of vector PQ or vector QP depending on direction. Let's suppose it's PQ. In that case, the coordinates of that would be P1 minus Q1 for x and P2 minus Q2 for y, and calculating the norm is pretty much the same as this formula, okay? And then the square root out of that, okay? So this is Euclidean distance, okay? And we can use that as the distance function and, again, as a similarity function. Another similarity function is the Manhattan distance, okay? This is I don't want to say it's very similar to Euclidean distance, but again, we can think of it as, for simplicity, we can think of like two-dimensional space, like Cartesian, like 2D kind of coordinate system. And what we're going to say is that, well, what if we turn this coordinate system into like a grid, okay? And what we're going to do is that we're going to basically impose a constraint that we cannot really go from, like, let's suppose this is P and that is Q. We cannot go from P to Q directly. Because we have this grid, we cannot really go inside the grid or go inside these like squares that it kind of creates. We cannot go inside, but we can move across like these borders, okay? So we can move across the sides of these squares. But again, we cannot go inside. We cannot go like using this kind of a diagonal kind of an approach. Neither this way nor that way if we wanted to go that way, let's suppose. I don't know if we go this way and that way. That would not be allowed either. So we can only go using these straight lines, okay? And that, of course, also gives us a sense of distance, and that's called Manhattan distance. And that is computed as the sum of the absolute values of the differences between the coordinates. In this case, again, these are feature vectors or feature tensors, but we can think of them as points on the high dimensional space. And how can we do that? Well, we can return. You can see the formula here. It's the difference. So we can do T1 minus T2. The order does not really matter because we're doing the absolute value of that. And then we sum that. Okay, let's comment that out. Okay, now we have the Manhattan distance computed. Finally, I also want to go over the cosine distance, and that is this is the formula right here. But let's think. Let's look at the. Let's think a bit more visually here. So let's suppose we have two vectors. Okay, this one and that one. Okay, it does not have to be a vector. It could be two lines. But usually when talking about cosine distance, well, talking about cosine similarity, cosine distance, we talk about vectors. At least in math, that's what we do. But in CS or in ML and DL, we don't really need to talk about them in terms of vectors. But I think it's important to know that they come from really vector math. Anyway, so. What cosine distance or cosine similarity gives us is the degree of similarity between two call it tensors, feature vectors, and that is quantified by the cosine of the angle between these two tensors. Let's suppose, again, we use these terms tensor, feature vector, and vector interchangeably. So let's suppose we have these two here, okay? Well, then we have some angle between them. Notice that if the angle is 0, they're the same pretty much. They're across the same line at least, okay? They might not be exactly the same, but they will be across this. They'll pretty much be, one is going to be on top of the other, okay? And if the magnitudes are the same, then they're exactly the same, okay? So what this angle is going to tell us is how similar these two lines are in a way, two vectors are. Okay, if the angle is 0, they are the same pretty much, right? So that's basically the way cosine distance works. We will find the cosine of the angle between these two lines. And if the cosine is 0, that means if the value is 0, it means they're not very similar. And if it's 1, it means they're very similar. And cosine of angle 0 is actually 1, which means that, well, again, if the angle is 0, they're going to be pretty much the same line. And cosine of 0, conveniently, that's 1. Okay. So how can we implement this? One way to do it is using this kind of a formula here. Cosine of theta is a times b over magnitude of a times magnitude of b. Okay, this is the formula right here. Let me zoom in. Okay, right here. Cool. And yeah, it seems like Wikipedia does not really play nicely with this zoom, but this is the formula we want to implement. Cosine of theta is a times b, so the dot product of a and b over a times magnitude of a times magnitude of b. Now, one thing to note about cosine distance is that for zero tensors or zero rays, whatever you want to call it, if every element in T1 is 0, it is not really defined. It's undefined. So to make sure that none of T1 or T2 is a zero tensor, what we can do is that we can say NP count non-zero of T1 times T2. Now, remember that this is going to be an element-wise kind of multiplication. And if T1 or T2 has actually, what would be a better way? I think the multiplication itself may not be the best. I think what we can do is that we can verify it this way, or NP count non-zero T2. So if this doesn't equal 0, if this equals 0 or that equals 0, we're going to raise maybe, I don't know, like a value error. Cosine distance is undefined for 0 tensors. Something like that. Okay. Otherwise, what we're going to do is that we're going to return a times b, okay, that's the dot product, T1 dot T2, over the magnitude of T1, NP, linolog, norm of T1, okay, times NP, linolog, norm of T2. Now notice that we use the magnitude of a feature vector in this case. There we also use the magnitude because we wanted the size of the hypotenuse pretty much, and we found the hypotenuse by pretty much finding the vector first and then then finding the magnitude of that. Here we find the magnitude of the tensor T1 and tensor T2 directly. We find these magnitudes pretty much directly using NP linolog norm. Okay, and now we have that distance as well. We have the cosine distance. Now, these are some random values, and we're going to get the same results over and over again because we have a random seed set for reproducible experiments. But for a better kind of a visualization here, let's change T1 and T2 to like more reasonable numbers, like 3 and 4. And the other one, well, points, sorry. T1 is 3, 4, and T2 is 0, 0. In this case, we're on like Cartesian coordinate system pretty much. And because T2 is... actually, if we run this, we're going to get a value error. Cool, because T2 is a 0 tensor, and cosine distance is not defined pretty much for those tensors. Let's comment this out so that it does not interfere. Now, notice that Euclidean distance between the center and point 3, 4 is 5, and it should be 5 because we have this right triangle with the sides 3 and 4, and we get the hypotenuse, which is the square root of 9 plus 16, square root of 25, which is 5. Cool. So we can verify Euclidean distance. That's kind of that the implementation is right. Of course, we would need a lot more tests, but for a simple kind of a verification, more of a visual verification, that should be fine. For Manhattan distance, we have 0.0 and then 3, 4. We got 7, of course. I mean, 3 is here, 4 would be somewhere there, and to get to that point, of course, we need to go 3 to the right, and then we need to go 4 up, so that's 7. Or we could have gone this way as well, like 4 up and 3 to the right, and so that is 7. And so, yeah, we got 7 there as well. And once again, the cosine distance is undefined because we have the 0 tensor. Okay. All right. So this is all I wanted to say about these 3 different similarity functions. Of course, this was more of a brief exploration or discussion. I thought it would still be helpful to have this to have these implemented. Again, it's pretty much all of them are like one-liners, and even here, I mean, if we commented this out, we would get probably like division by 0, nan, whatever. Because again, if we have a 0 tensor, its magnitude is also 0. Magnitude of this is 0. It's square root of 0, square root from 0 squared plus 0 squared, and so we'd get a division by 0. But all of them are pretty much one-liners. Kind of simple similarity functions, and they're used a lot. Like cosine similarity used a lot in natural language processing, super cool distance function. And one thing to note is that if these values are normalized, let me actually show you. I want to show you that as well. If T1 and T2 are normalized by the magnitude, sometimes you'll see what's known as normalized embeddings. And actually, cosine distance, it is equivalent to the dot product if we normalize these by their magnitudes. Their respective magnitudes here, T1, NP-log norm T1, NP-log norm T2. If we rerun this, remember cosine is this value, the same value, okay? I pasted it here, so I copied the thing. So, yeah, if the embeddings are normalized, then Euclidean distance is pretty much the same as the, the dot product is the same as the cosine distance pretty much, or cosine similarity. So yeah, thanks a lot for tuning in. I hope you found this helpful. If you have any questions, please feel free to comment in the comment section. And I'm going to see you next time.